Now, suppose that you have determined that the runtime of your algorithm is 2 times n to the power of 2 plus 10. The question is your algorithm big O of n to the power of 2. And in order to show this, like formally to show this, you would have to find a constant c and a small input size n0, such that for all n greater than or equal to n0, the runtime of your algorithm is bounded from above by c times gn. And you can easily show this by choosing c equals 3 and n0 equals 4. So if you set c equals 3, then you can easily see that 3 times n to the power of 2 bounds your function 2 times n to the power of 2 plus 10 from above. And you could easily set like your minimum input size to 4. And this relationship obviously holds for n0 equals 4. Like for input sizes more than 4, 3 times n to the 2 is higher than 2 times n to the power of 2 plus 10. You could also choose different values of c and n0, so you don't have to stick to, like I said, c equals 3 and n0 equals 4. You could select like c equals 7 and n0 equals 2. So if you select c equals 7, then the function 7 times n to the power of 2 bounds 2 times n to the power of 2 plus 10 from above, but only for values of n that are greater than 2. So by setting c equals 7 and n0 equals 2, you have your relationship once again. So you can describe this runtime function as big O of n to the power of 2. So suppose the takeaway message is, suppose you have determined that the runtime of your algorithm is t of n equals 2 times n to the power of 2 plus 10. The question is your algorithm in big O of n to the power of 2. The answer is yes. And you could use many different choices for c and n0 in order to show this. Now, another point is, let's say that you have found out that your algorithm has a runtime of n. You could also say that the upper bound of this algorithm is big O of n to the power of 2. And you could easily show this by setting c equals 1 and n0 equals 1. In this case, for all input sizes n greater than 1, n to the power of 2 is greater than n. Now, let's say you have determined that your algorithm has a runtime of 100 times n times log n. You could also say that this is in big O of n to the power of 2, but you would have to set the minimum value of n to be 1000. Only for values of n greater than 1000 does it hold that n to the power of 2 is higher than 100 times n times log n. And these are some code examples for big O classifications. When you're adding two numbers together, like you're adding b plus c, this has a constant order of growth of big O of 1. Let's say you have a while loop where n is decreased, like it's cut in half at its iteration. This is the kind of code that gives you a logarithmic runtime, log of n. Now, let's say you have a loop for the classic loop for int I equals 0 to n. This gives you a linear runtime of n. Now, the kind of algorithm that would give you an n times log n runtime is various sorting algorithms like merge sort, and various algorithms that use the divide and conquer coding paradigm would also give you an n times log n order of growth. The case of a code with a quadratic runtime, i.e. an n to the power of 2 runtime, are nested for loops where you have an outer for loop from for I equals 0 to n with an inner for loop for j equals 0 to n that gives you a quadratic runtime. A cubic runtime would be given by a triple nested for loop, and then an exponential runtime, which is 2 to the power of n, would be given by some kind of algorithms that perform an exhaustive search. Obviously, exponential runtimes are not desirable ones. And just to recap, big omega is a lower bound on a function. In the case of big omega, the relationships between t and z have been reversed in this case, but the c constant and the n0 value that you're looking for basically remain the same. So you're looking for a constant c and an n0 value such that you can describe a lower bound on your runtime t of n. And this is how CLRS illustrates the asymptotic big omega notation. You have a function of n that describes your algorithm's runtime, and then you have a lower bound function c times g of n, which essentially places a lower bound on f of n. And we say that g of n is an asymptotic lower bound for your function f of n. An example of big omega notation is, for example, you might say that a function that performs square root of n steps is big omega of log n. And in order to illustrate this relationship, you could choose c equals 1 and n0 equals 16. And in this case, you could see that for input sizes more than 16, the function log n is always smaller than square root of n. So that illustrates the lower bound relationship that log of n has against square root of n, and therefore you say that square root of n equals big omega of log of n. And big theta means both big O and big omega. So you simply say that your runtime f of n is big theta of g of n if and only if you have both a big O and a big omega relationship between f and g. And your leading the constants and low order terms once again don't matter in order to substantiate this. And this is how CLRS illustrates the big theta notation. You have a function f which describes your program's runtime, and g can serve both as an upper bound for f and as a lower bound for f if you pick the proper c1 and c2 constants respectively. So an example of a big theta case is, let's say you have described your program's runtime as n to the power of 2 over 2 minus 2n. You could say that this is big theta of n to the power of 2 if you set minimum data set size of 8, and then you set c1 equals 1/4 for your lower bound and c2 equals 1/2 for your upper bound. In this case, the same n to the power of 2 function can serve both as an upper bound and as a lower bound for your runtime function. And finally, when you're dealing with polynomials, let's say you have a polynomial of degree k. So you have your polynomial p of n, which is described by a number of factors all the way up to a k times n to the power of k. Then it is always the case that p of n equals big O of n to the power of k. And you could formally prove this by choosing n0 to be 1 and choosing your constant to be a0 plus a1 plus all the way up to ak. And then you could prove that for all input sizes n greater than or equal to n0, your p of n is less than or equal to your constant c, which you have chosen, times n to the power of k. So therefore, your polynomial function is big O of n to the power of k. For example, let's look at this polynomial function, t of n equals 1 plus a number of factors all the way up to 0.5 times n to the power of 3. Then it is not big O of n to the power of 2, but it is big O of n to the power of 3. As you can see, n to the power of 3 is an upper bound for your polynomial function when you go to high values of n. And you can also easily prove that n to the power of k is not big O of n to the power of k minus 1, and you could prove this by contradiction. If you suppose that this were true, then there would be c and n0, so that n to the power of k would be less than or equal to c times n to the power of k minus 1. but that would imply an upper bound of n of c, but you know that this contradicts your assumption that n has to be greater than n0, so that cannot be the case. So it cannot be the case that n to the power of k is big O of n to the power of k minus 1. It can only be the case that n to the power of k is big O of n to the power of k, as illustrated in this plot, where the polynomial function is big O of n to the power of 3, but it's not big O of n to the power of 2. So the takeaway from this lecture is, if you want to prove that T of n equals big O of G of n, you come up with constants C and n0 so that the definition is satisfied. And if you want to prove that Tn is not a big O of a function, you can use proof by contradiction, where if you suppose that someone gave you constant C and an n0 bound so that the definition of the big O was satisfied, so that this is not possible. And as a takeaway message, it is important to always keep in mind as computer scientists what the big O notation means, because this is how computer scientists discuss the scalability of algorithms, and it is also something that an interviewer will ask in an interview coding question, and they expect you to be able to do the asymptotic analysis of the algorithm that you're proposing.